Well, I'm Annika. Thank you, Annika, for the introduction. Department manager at Veoneer, and responsible then for the vision algorithm development here. And we develop then detections of traffic and infrastructure, for example, pedestrians, road lanes, road boundary, traffic signs, and so on. And I myself have been working in this field for machine vision for about 25 years. And I've also done some research in the area in Linköping University then. Now, next. So just to give you the context I'm working in. By showing you this Veoneer technology showcase and the products we develop and sell them. We develop the products for active safety in cars. When it comes to artificial environments and artificial data, the vision systems and the night vision systems are most close to us, to my area, but also the radar and LiDAR systems benefit from artificial data, and all is connected in the brain of the system, the ADAS ECU, the control unit, and of course in this development we also have use for artificial environments. Let's see if I can. If we look in the data needs in our systems, traditionally the automotive industry base all the trust in our systems in statistic verification or collected on data collected by driving. So we drive a lot and we record a lot. And the gray arrow in this picture, it shows the scale of the system solutions from small cars with more cost-efficient solutions to advanced systems in luxury cars where automated driving is supported. And these NCAP systems, the new car assessment programs, it's when new cars are tested in different aspects of safety, and therefore it defines the performance needed in our vision systems to reach the different levels of safety aspects from up to 5 stars then. And in the highly autonomous driving systems, the HUD systems, the safety aspects here, it requires increase the required amount of data quite significantly. So it's illustrated then by the blue arrow. And just to give you a feeling for the amount of data we are talking about, an NCAP systems is maybe counted in 1 million of driven kilometers. But the HUD system, we are talking about many millions of driven kilometers that we would need to record in the traditional way when we verify and develop our systems. Yes, and here is a typical important case when developing active safety systems. Something is appearing in front of a vehicle and we need to make a decision to brake based on the detection and classification of the object in front of the car. And this movie is old. It was made already in 2009 when we were working with detection of animals with a night vision system. So part of this work was done in collaboration with the Swedish Defense Research Agency and also a Vinnova project. And as you can imagine, it's a fake. So the close-up deer here is not a real one. It's a made-up one, and the more distant one is a real one. And I apologize for Zoom maybe transferring this video not in a perfect way, but I hope you can see some part of it at least. So when is synthetic data valuable for us? Well, it is in these near collision events, which we saw in the previous picture. A vulnerable road user is running out in front of a car, maybe getting out of his car on the highway, changing tires. Maybe we are driving in the wrong direction. And scenarios and data like this are very difficult to encounter in real driving when we collect the data. It requires huge amounts of driving to find these cases. And we anyway need this data to train our systems and to get a good performance in these critical scenarios. And we did a lot of different sets of data, of course, to verify our performance. And to set up a recording like this, it would be dangerous to the involved persons. So here is one area where we would really is useful with artificial data. Another use case is what you see in the upper right corner. It's the ground truthing case. We could, with synthetic data, perfect ground truth is achieved, of course, because we already know what is right or wrong in the picture. And thereby we could reduce the number of manual annotations needed anyway, and decrease the cost and the time spent on the data before we can actually use it. And the final case I have here in this introductory picture, it's the closed loop testing case. So we need to do some closed loop testing, and here artificial data enables us to create a lot of variations that we need in the pictures, details or weather conditions, and maybe new cars or new traffic signs and so on. And this is also one thing that could reduce the amount of driving for us to introduce all these variations. If I go into a little bit about the alternative that we have for ground truthing, it is of course to use other reference sensors for the ground truthing. And in this example, we see a recorded image up to the right, and then we have a ground truthing image created by a LiDAR system in the big picture. So in this area, we have used the LiDAR to create the bounding boxes around the cars. And of course, we could also use other reference sensors. But there are also always technical difficulties when using reference sensors, technical challenges with these. A simplification is very much looked forward to. The traditional way is, of course, to manually draw in the images, to draw the bounding boxes and to point out all pedestrians or signs. Of course, this can be developed further by using AI to auto-generate the bounding boxes in the pictures. But anyway, you would need to verify the quality in this ground truthing manually. So as we saw in the last picture, an artificial image has this ground truthing challenge or problem solved at no cost for us. So what details need to be simulated then? We have also seen in previous talks, the first talk on simulation engines, and of course there is a lot of different simulations engines that can simulate on different detail level. Here we have examples in the top or in the bottom right image is simulated image that is used for real-time simulation. And the top image to the right is a simulated image with a lot of details added that would be very good to use in training or verification of the systems. You will probably hear a lot more of these this type of image in later in the afternoon in Professor Jonas Anger's talk, as this comes from the Synthscapes. And the questions here is what details that really needs to be simulated for what purpose? If it is for actually detection development, or if it is for verification of scenarios and features. So going back a little bit to the closed loop generated scenario, how does it look like? So this is another example of a generated scenario that is possible to use in a closed loop verification. And when I say closed loop, we mean that we have a feedback loop between the sensor, the camera sensor, and the car movements, so that the speed of the vehicle and the movements is also taken into account when we do our testing, that it's really acting in the way that we would like it to. So a movie like that in the normal scenario could be injected into the camera, into our test systems. And then it looks like the picture to the right. And here we see the detections that are done around the vehicle, and also the distance in the detection outmost to the right. And also the field of view of the camera. So on feature level, when looking at scenarios and scenario testing, this is fine. But the question is, when we really are working on the algorithm development and the detection of a pedestrian or a lane marking, if this is really enough. So I will move on to these kind of details instead. So this picture, it shows a little bit on experiments that has been made on simple augmentation in real images, and to create the variation where we actually back data for our development. And these experiments were done in the department. So in one of the pictures, you see some pools of water that could appear like after a shower of rain. These, of course, cause interesting things in our detection sometimes. And we have also in these pictures tried to make the road look wet or damp, which is another difficulty to encounter. And we have generated some artificial tar marks in roads that can be confused with the lane markings. And one of the challenges that we have seen when generating variations or simple augmentation in images like this are the ambient lighting. So in the case with the water puddles, you can struggle with making it look real to the eye and to see how you project the sky mirroring in those water puddles to make it actually look like it was a realistic image. And that could be a challenge. And in the tar marks example, you see in the bottom left image that it's clearly seen that it is an artificial tar mark, because the light shining on it is not maybe the realistic one when you have a shadow from the tree falling over this tar mark. And also in a rainy situation, how to apply these realistic scenarios to the fakes that we are introducing in the images. And here the question is then, what is really needed? What level of realism is needed in the picture? I mean, it's easy to see for our eye that this is fake or included in the real image behind. But is it really needed when we develop when we train our algorithms and develop our CNNs? Or is it, when can we actually stop making it look realistic and still get the performance that we need? And the other question that we have when doing these kind of augmentation is to how do we balance the training time with the augmentation level and the variation of these images with the performance. I mean, we can add a lot of details and a lot of variation, and it increases the training time quite significantly. So here we have a trade-off between performance and training time. So when in industry and under development, we always have a car rollout program to consider and the delivery time to cope with, and we need to spend the time wisely on this. And I have come now to a final case when it comes to the CNN performance aspects in our development. Of course, when we use one sensor and one sensor characteristics in our training data, we tailor our CNN towards that sensor. And each data sample will be more valuable, and it allows for a higher performance on this product and this sensor type, maybe. At least if we have a well-designed training set. But if we allow for more sensor types in the data set, we could reuse earlier data collection, of course, that we already have collected. And we can also use, which is obvious that we need to do, synthetic data in the training set. And thereby, of course, we reduce the cost of each data sample, and we would make the data set more allowing for robust for changes in the sensor characteristic. For example, when the sensor is aging, or if we have physical characteristics on the sensor affecting the data. So this is one of the questions that we are also considering to design our training data set and how that affects the CNN and the performance of our systems. So of course the challenges when doing this could be like we have a different field of view, and we have a different sensor resolution, and we have a different exposure time, and so on to consider in these aspects. So with coming to the summary here, I have shown you a little bit on examples only on when we have use for artificial data and artificial environment in our development in automotive industry. And our purpose is, of course, to create trust and to minimize accidents. These near pass collision data are difficult to encounter and is really needed in our development. And we need a lot of variations in the scenarios to ensure that we have tested all possible aspects when we go out on the road. So the area is really huge, and we continuously work with the question of defining in what cases we would need real data and not only artificial data, and how to balance the performance then using real data. And I think this research community can be of great support to us and answering some of these questions that we have. And with that, I would like to close by thank you for the attention and see if there are some questions in case I was talking too fast.
Thank you so much for a very nice and clear presentation. I didn't think that you spoke too fast. There is a question, I don't know, I think that you touched upon it a bit. It seems that the data simulation described so far are designed rather than learned. And then the question is whether you see the prospect of actually learning to design the data.
Learning to design the data set that we would need. Is that the question? Or
yes, precisely generating basically the synthetic data.
Yeah, I think
something
it is.
that is just around the corner for you.
Yeah, I think if I understand the question correctly, I mean it's both of designing the data set, of course. A wisely designed data set is very essential when doing the training, and then of course we try to suppress the flaws that we see in the detections by adding details where we might have problems.
One question that came to my mind, of course, has to do with safety and standardizing, you know, self-driving cars in terms of saying that, how do you see that evolving? How can you say that you have basically enough data, enough situations, or will that never be the case?
Well, safety is very important to us, and in case, of course, there are measures in our systems to alarm the system, the car system, if we consider ourselves or our detection of not fulfilling the standards or not being safe. Actually, there is a flag: safe, not safe. So yes. And this is, of course, why we need all this data and all these variations to ensure that we can build the confidence and the trust that our detections can be reliable. But safety when going to autonomous driving is, of course, a huge aspect, and I prefer to look at in the ways that the most important to is actually to prevent accidents by detecting these critical scenarios.
Right.